Okay, so let's continue. So we have now 3 theory talks, and next speaker is Jim Freericks from Georgetown, and I think he will tell us a lot of interesting stuff about the spectrum of ions and 2D crystals.
Well, some of that is going to come tomorrow, but today I'm going to focus on an idea that really comes from Wes Campbell on how to try and do some spectroscopy in the spin models that you get from an ion trap quantum simulator. And the brunt of the work has been done by a graduate student, Bryce Yoshimura, who's a beginning graduate student at Georgetown. He has a fellowship from an organization called ARCS that I actually don't know a huge amount about, but I'm very thankful for the fact that they're supporting him. This work was started within the DARPA OLE program, and it's now being transitioned into being supported under NSF. John gave a nice introduction to the Penning trap, and so I'm not going to go into great detail about exactly how everything works here because he went over it in much more detail than I'm going to have time to now. The main point is that you have a two-dimensional crystal of ions. It's a rotating crystal. We've been able to benchmark what's coming out of the experiments with theory. This is calculations for what the interaction strengths are as a function of detuning as you're changing the power law. And the dots are the data and the lines are fits of the data to different power laws. So in the extreme limits where you're detuning right on the center of mass mode or you're detuning very far from the center of mass law, the power laws are much more accurate. In the intermediate regime, they're really only approximate. And so you can clearly see some deviations here. And then this is the data that John also showed comparing the average value of these interactions to the mean field theory measurements that they were doing because the interactions are relatively weak. And you can see we have good agreement. There are no adjustable parameters in here. The fuzziness on the red line is to try to indicate some level of the uncertainty in the parameters that went into the theory from the measurement of the experimental data. And then the other platform that Phil gave a very nice talk on yesterday is the linear Paul trap. And here the experiments are quite a bit more advanced because we're really doing simulation. In the Penning trap, we still haven't gotten to the point where we're actually doing a simulation. We're just to the point where we're setting up the experiments so that we'll be able to do the simulation hopefully soon. So the model that's being simulated that most people are familiar with is a transverse field Ising model. So there's some interaction. There should be an IJ subscript here. There's an interaction between the spins at two different sites. There's a magnetic field. The magnetic field is changing as a function of time, so the whole Hamiltonian is a function of time. And this is a schematic for how one does that. One turns on the interactions. They remain constant as a function of time. And then one has a magnetic field that's ramped down from a large value where you prepare the system in an eigenstate that's directed along the magnetic field, and then to a very small value where you then will adiabatically evolve into the ground state of the Hamiltonian without the magnetic field. And then experiments have been done now up to about 16 ions, and Phil showed you these experimental results here. Now, Phil mentioned this as well. There's a time window over which you can run these experiments, which is set primarily by some decoherence in the system. And that decoherence time, even if your single ion decoherence is in the order of seconds, when you put a lot of them together, your decoherence times get much, much shorter. So there's a finite limit as to how long you're able to actually run these experiments. And given the strength of the interactions, it turns out that it's very difficult to run these experiments in such a way that you really are adiabatic. So you're almost always creating diabatic excitations within the system. And one might think that this is a bad thing, but actually we want to turn that into a good thing because for many correlated systems, it's actually understanding the excitation spectrum above the ground state that's a very important problem. And so this actually will allow us to learn about the excitation spectrum and about the low-lying eigenstates. So the key is that you have to create the excitations, and that's automatically going to happen in any experiment. So the idea that we have, as opposed to doing a modulation spectroscopy where you're modulating something like a field and looking for a resonance, what we're doing is just looking at the evolution of the system as a function of time. So if I have a collection of eigenstates that have been excited into a linear superposition, when I look at an expectation value of something that involves that superposition, I will see oscillations that are coming from the energy differences between the different energies of the states that I have excited. And I'll primarily see excitations from the dominant state, which is the ground state, and the low-lying excited states. And that's the basic idea that we're going to have for this. We want to find a protocol that we can use to try to carry out this kind of spectroscopy. We'll get a time series, and then we'll just do effectively a Fourier transform on that to pick out the frequencies that are present in the signal. So the idea is that we run through the experiments exactly the way that they're done, knowing that we're going to diabatically create excitations. And then at some point in time, we fix the magnetic field and stop. And then we just hold it at that value and run the experiment for a longer period of time. This is the period of time where we're collecting up the excitations. And then we're going to just sample at different times to create a time series measuring a particular expectation value. So in the work that I'm going to show you, we're going to be measuring just the probability of the highest probability state as a function of time. And just to give you a little teaser right now, this would be an exact signal is the black line, and then the red line would be a simulated data that has a certain amount of noise on it. Then we want to do a Fourier transform of that, signal process it, and pick out the peaks, which are going to tell us what the excitation frequencies are. We then repeat that at many different magnetic fields, and hopefully we can then map out some kind of an energy spectra as a function of the magnetic field for the system. How far up you're going to be able to go in this plot is going to be determined by how many excitations you make. And you have to be careful about how many you make, because once you start getting excitation energy splittings between these that have large levels, it becomes more difficult to analyze your data and understand what the actual spectra is, reconstruct the full spectra. The test case that I'm going to talk to you about is infinite range transverse field Ising model. We're doing this for two reasons. One is this is an important test case for the Penning trap, because the Penning trap has so many spins. This is one of the few cases that you actually can get numerics to try to benchmark the Penning trap. In this case, the total spin s squared is a good quantum number, and so the Hilbert space shrinks from 2 to the n just down to n plus 1 for each of the different spin sectors. And for one of the signs of the interaction, the ferromagnetic state is the ground state. So that's the one that I'm going to study, where the matrices that we have to look at are just n plus 1. We're going to be working with n equals 400, so our matrices are not very large. And the one thing I want to point out is that there is a spin reflection parity in this model, which means that the states can be classified as even or odd. That's the difference between the red and the black curves here. And when we do a simulation, we really are restricting ourselves to one of the symmetry sectors. So if the ground state is the symmetric one that I'm working with, I'm really only going to be able to pick out the black energy levels. None of the red ones are going to show up because they're not connected to each other via the Hamiltonian. Now, the first step that we have to do is we have to calculate the time evolution. Because it's a time-dependent problem, and it's a non-trivial time-dependent problem because this Hamiltonian does not commute with itself at two different times, because the value of this B field is changing, and this term does not commute with this term. So we have to evaluate this via a time-ordered product, and it's easy to write down. It's easy to figure out how to do it via Trotter decomposition as well. In this case, what we do is we discretize our time into a bunch of different steps, delta t, and then we evaluate the time evolution over this very short interval by effectively just approximating it by the Hamiltonian at the midpoint of the interval, and then just assuming it's constant over the interval. So we just multiply by a delta t times the Hamiltonian at the midpoint of this interval. And then you just build up your different factors. This is your initial time, second time, third time, etc. And you build up your factors in a time-ordered way. And that's one of the ways that you can construct the time-ordered product. Now, if you do it that way, you got to make your delta t really small, because you can get significant errors in doing that. And it turns out with very small additional work, you can improve the error very dramatically. And I want to mention that although at this point we're using this in a numerical calculation, it's quite possible that this kind of an idea, which many of you might not be familiar with, so I'm going to just spend a little bit of time talking about it, could be useful if you want to apply your Hamiltonian within the ion trap in a stroboscopic way. Because the typical way that it's done stroboscopically is the way that I just showed you on the previous slide, but you might actually benefit with perhaps just slightly more work to generate it in a way that you have much smaller errors. The idea for how to do this is there are two different ways that you can express a time-ordered product. One is a Magnus expansion, and the first order term of the Magnus expansion ignores the fact that you have time ordering. You just integrate the Hamiltonian and then take the exponential of the integral. And then there are correction terms that involve commutators of the Hamiltonian. And the other one that you can look at is the Baker-Campbell-Hausdorff theorem. If you look at combining those Trotter terms together, you get additional commutators amongst the different terms that you have to take into account. Now, if you take one of those factors and instead re-express it in terms of two factors with a smaller value of delta t, you can cancel the effect of these non-commuting operators with a very particular choice of the delta t's and of the weights that you put into these factors. Now, I don't have time to go through the algebra for this. There's a very nice paper here in the New Journal of Physics that just came out last year. The technique is called a commutator-free exponential time propagation, so they call it CFET. And what it basically says is you take that product of two evolution operators, and instead of evaluating at the midpoint, these operators here, this is the Hamiltonian evaluated at time 1, Hamiltonian evaluated at time 2. Time 1 is not at the midpoint, but it's at 1/2 minus the square root of 3 over 6. Seems like a crazy number. And the other point is 1/2 plus the square root of 3 over 6. Also seems like a crazy number. And then the weights that you put on here are not unit weights. They're weighted in this fashion with these two different factors. And if you do this, then you find that the error goes like delta t to the fourth. It actually cancels out a lot of the issues that come from non-commuting operators and so forth. What we actually use in our calculation is a slightly more complicated scheme that cancels errors up to delta t to the fifth. Okay, so as I mentioned before, some of these ideas might actually be useful for those of you that want to apply Hamiltonians in a stroboscopic way, because you might be able to gain a lot of accuracy in the application of the Hamiltonian with very little extra work, assuming that you have the ability to adjust the times at which you are applying the Hamiltonian, as opposed to having to do it at an equal spacing that's already set. Now here's a plot of it's a false color plot of the probability of the states with different SZ values as a function of the magnetic field that I'm ramping down. So I start with the magnetic field way over outside the window, and as I start ramping it down, the SZ values are primarily clustered around 0. And then when I hit the region around where the minimum gap is, that's when I have this bifurcation, and I go into the ferromagnetic state of the system. So this is what you get for an adiabatic evolution. This is what you get for a diabatic evolution. It's pretty much the same, except you can see there's some additional oscillations that are present due to the fact that you're evolving the system too rapidly. And one of the things that we thought was important within this project was to make sure that we talk about real experimental situations. So I could have just generated some curves without any noise, without any decoherence, done nice Fourier transforms, and everything would have looked beautiful. But it might have been useless if you want to actually try and apply this into a real system. And so we're really thinking about taking experimental data and applying it. And so we have to look at we've looked at two of the issues that are going to come up with that. One is the fact that there's going to be decoherence in the signal. And for that, we just multiply our signal by an exponential decay multiplied by some decoherence time, which is quite a bit longer than the actual time window over which we're doing the experiment. And then we just add noise by doing Poissonian statistics. And in this case, some of the experimentalists might start groaning about this, but we are taking a lot of data. So we're assuming that you're taking about 10,000 data points for each time window, because you typically are going to find your highest probability might only be on the order of 1% or so. And so you're going to have maybe on the order of 100, 200 data points for the highest probability state, which is the one who you're looking at the oscillations for. So you have to do a lot of experiments, you have to do a lot of measurements to generate the data, because the events end up being rare when you have lots of states. And when you do that, you get a signal that looks like this red curve here. It's supposed to be giving you, it's based on this exact curve, which is the black curve. And you can see, I'm not including very many periods here, and I'm trying to extract the data. What you will see with the signal processing technique that we're going to use, you actually get a fit that's given by this green curve. And so you can actually fit that data and compensate for that noise quite well. And I'm going to talk to you a bit about how that's done.
What was the vertical signal?
This is just probability of the highest probability state. Okay, so we picked which state at this given time is the highest probability, which is what we can pick out of here. We just find the state here that's closest to orange, and then from that state we just look at how it evolves as a function of time. Okay, so most of you probably know more about Fourier transforms than I do. I'll just tell you a little bit about what I know about Fourier transforms. So one of the important things is Nyquist's theorem. And Nyquist says that if I take n equally spaced time steps of width delta t, then I can determine a Fourier transform accurately for frequencies that are smaller than 1 over 2 delta t. Okay, and I'll show you a picture on the next page as to why there's a restriction. You can't determine the high frequency behavior. Shannon went a step farther and proved that if the Fourier transform is only non-zero within a finite window, then it can be found with a time sampling that satisfies delta t equals 1 over 2 times that maximum frequency in the finite window where the Fourier transform sits. Okay, that might be a little bit more counterintuitive, but it tells you that if I don't have the high frequencies, I don't need a lot of sampling in order to determine what the shape of the Fourier transform is going to look like. Now, why is it that you have problems with high frequencies? At high frequencies, what happens is, so here are two signals. There's a black signal and there's a dash signal. And you can see if you sample only at the points with the arrows, the sampling is exactly the same. The two curves look exactly the same, yet one has a much higher frequency than the other one. And so this error is called aliasing, and you cannot tell which one of these is what your signal is. So when you have a discrete sampling, you're actually putting in a high frequency cutoff to your Fourier transform because you can't tell what's happening at the higher frequencies. And this is the effect that gives rise to the fact that there's a Nyquist frequency and so forth. Okay. We're not actually looking for a Fourier transform. We know we have discrete frequencies. So we're really looking at a Fourier series, not a Fourier transform. When I have a Fourier series, there's far less information. Let's say I had 10 frequencies. I essentially have to determine what those 10 frequencies are and what the 10 weights are. That's 20 sets of information that I need. I should be able to determine it with much less information than what Nyquist says. And this is the whole idea behind what has been called now in the signal processing game compressive sensing. So it's been introduced. There probably are 100 different algorithms out there for compressive sensing, and I can't tell you that I fully understand even one of them. But there's lots of packages out there that you can get that will tell you how to do it, and the main thing that they can handle is they take care of the noise kind of like a black box and spit out for you the frequencies and the weights so that of the discrete Fourier series that you're trying to sample. And there is a little bit of an art to figuring out how to tune the parameters that you have to put in to tell it how to do its job, but it's a pretty robust numerical technique. So now let me explain to you how we're trying to do this. We're thinking about measuring, we're assuming that in an efficient experiment you can measure about 100 different runs per second. That's assuming that at most you're running over a full run of taking data and then setting up for the next run isn't going to take more than about 10 milliseconds. We're going to measure 10,000 probabilities at a given time step. That's going to give us about 100 measurements if our probability is 1%. We're going to repeat for 200 time steps. And it turns out if you're actually interested in getting discrete frequencies rather than a Fourier transform, it's actually better to choose your time steps randomly rather than equally spaced. It will give you a better result for your data. And this will require about 6 hours of time for generating the data for one B field. Okay? And now here is some data. This is actually, I think, quite a bit more time steps than the 100 time steps. This is just illustrating if you work a lot harder and take a lot more data, then you can get actually signals that look like this, which you can just do a Fourier transform. When you do the Fourier transform, you see a nice noise floor here, and then you see sticking out of the noise floor are these three nice sharp peaks. And so those would be the energy values that you're pulling out of the spectroscopy. That was not data that was processed with this compressive sensing. Now I'm going to show you a series of data that has been processed with this compressive sensing. And we're starting at a value of the B field that is very close to the minimum gap of the system. This is where the different energy levels have evolved to in the system. We still have predominantly the highest probability state around SZ equals 0. This is what the data looks like when we've put the noise on. This is the Fourier transform. The red curve is the Fourier transform just of the data with the noise. The blue lines are what the exact energy eigenvalues are supposed to be, and the green dots are what comes out of this compressive sensing. So you can see, and then if you go back and you take the compressive sensing result and plot it as a function of time, you get the green curve, and it's supposed to be fitting the black curve, which is the exact curve. But of course I didn't input the black curve, I inputted the red curve. Okay? So it's doing pretty good at handling this noise. It is telling me that I've got a frequency. Now, whether or not there actually are two frequencies or one frequency, this is one of the issues that comes out with this processing technique that is difficult to determine. So this is going to, in essence, be some measure of the kind of errors that you're going to be getting in doing these calculations. But you can see it's nicely producing the first excited state. I could get a pretty good value for the energy of the first excited state by doing this technique. Now, as I come in a little bit further, I'm exciting more excitations. It's more diabatic. If you look, these probabilities here are going to start rising. I'm now centered around a non-zero value of the average z component of the spin. And it's giving similar kind of data. I'm getting one dot. It's not lying on the line. There's some systematic offset. And you can see the fit isn't perfect by any means. But I don't have a lot of data here. That's really the point. It takes a lot of time just to get this much data. And so we're trying to look at the feasibility of how you can do this. So now we can march along and look at some of the other values. Here, as the probabilities start to get a bit bigger and there's more structure in the signal, I can start to pick out a number of these different points for the spectra. That continues as I move farther along. Here I'm picking out these 2 points fairly accurately. Here I'm only able to pick up the lowest one, but I'm getting a very good fit of the exact results. And then here we're moving along. Here we're able to pick up the lowest 2, but not the furthest one. Here once again, here we have a spurious result. So sometimes this happens. Sometimes you get a result that is incorrect out of this. It's not something that is guaranteed to always work. I have data that isn't perfect. I might get results that give spurious results that come out of the analysis. Okay? So that's one thing that you have to be aware of when you're doing this. And here we're getting close to the point where it's made the transition into the fully ferromagnetic state. Whoops. I don't know why that came up. But you can see in all of these different cases we're doing pretty well. We're getting pretty good accuracy for the way in which we're able to see that data. Okay, so about 2 days ago, actually Crystal gave us data months ago, but about 2 days ago I got Bryce to finally analyze the data, and we haven't had enough time to put on what the correct results are. So I don't know exactly how accurate this is, but this is data that comes from Chris's group at Maryland. It's a 4-ion chain, and they're not measuring the highest probability state, they're measuring the magnetization as a function of time. And so I'm going to show you what some of that data looks like. So this is the time trace. The data is the black curve. It's a little bit noisy. The red curve is what we get after we fit it with the compressive sensing. And what we find, we're getting a whole bunch of different frequencies that are present in here. I don't know whether these are real or spurious yet, because it's a fairly simple calculation. You just have to have the interactions correct. We're going to work out what the correct energy level spacings are and see how accurate these results are. But this is looking now at real data for a slightly different quantity, the magnetization as opposed to the probability. And so there's a series of different results that we have here. And I'll just take you through a couple of them. So here the magnetic field is a little bit larger. Here it's twice as big. It's going up in steps of 0.125. You can see here the compressive sensing is interpreting a lot of these fluctuations as noise. So it's really just picking out smoother peaks, and so we're having fewer excitation energies that are being picked out by the technique. Just quickly go through a couple of these. Since I don't know how accurate this is, I don't have a lot of comments. It's really just showing you what the data is. But you can clearly see we're getting a number of different frequencies. In many cases, when you're getting these two paired close together, that's a pretty good indication that there's something happening right around these different points. And then I think that's it. So with that, I'm going to conclude. What I hope I have showed you is when you run an ion trap experiment and you do a diabatic creation of excited states, this is actually a very good thing because it gives you now a window into looking at things that are quite interesting in trying to understand the behavior of the many-body system. In particular, you're getting information about excited states. The ability to extract the frequencies is actually quite robust to noise. And this is a very important thing because it means that you can work with realistic experimental data that is going to be fairly noisy and still be able to extract the frequencies because there aren't very many frequencies in the low energy area. Now, it's going to become much, much tougher to do this, and it's going to require a lot more data and over a longer time window if you're looking at strongly frustrated systems that have lots of low-lying excitations. So at some point, this technique is going to fail when the system becomes big enough or is frustrated enough that I have lots of very closely spaced, nearly degenerate levels. Then those energy differences are very small, which means to see at least one period, I have to go out to very long time windows, and I can't go out very long because of decoherence and so forth. So this method isn't going to work for everything. But it is a technique that is going to allow you to pull out some interesting results about the spectra within these systems. And then the other thing I want to say is you can't just take the naive Fourier transform and hope that it works. You really have to look at these more sophisticated techniques of signal processing in order to be able to analyze data and get good results. Okay, and with that, if there are any questions for discussion, I'm happy to talk with you.
Okay, thanks, Tim.
You showed some real data at the end. Can you just analytically calculate the spectrum and compare to what you got there? Or?
It's very easy to calculate the spectrum. So I can analytically do it here at b = 0. And Crystal actually has already done this, and she gave me her data this morning. And I looked at these frequencies, and they're nothing like what her data is. So he has obviously scaled these frequencies to something, and I don't know what it is. So I can't directly compare just yet. But we'll have this sorted out in just a couple of days, and we'll see how well this technique is working at pulling out the different energies. Yeah, there are questions. You have a couple of options here. There's a question of, what observable is it that you want to measure? We thought that taking the highest probability state and looking at the probability was a good thing to try. Here they're looking at the magnetization. That's another kind of global quantity. That's also another good idea to try. There are other things that you might want to look at as well. The frequency differences should come into any of them. It doesn't really matter. What you want to do is find the thing that is going to be most robust. So the technique is a very general technique.
So I'm kind of curious what happens if you go to larger system size, and in particular, I think about a typical many-body system in this diabatic preparation regime. What I expect is to create a whole host of quasi-particles, right? Not just sort of single excitations. And of course, you're working with the full Hamiltonian here. So for you, an excitation is an excitation is an excitation. But if you think about it from the many-body perspective, there's a difference between two quasi-particles and one quasi-particle. And I'm kind of curious if you thought about the scaling of these techniques to that many-body regime.
So I think it actually becomes a second information processing problem that you have to sort through, which probably people that were doing spectroscopy in the late 1800s had to deal with, which is I'm getting a bunch of energy differences here, and I'm not really sure exactly what their energy differences with respect to. So there's a reconstruction problem to try and construct what is the energy spectrum that you have corresponding to this. So we certainly see when we do a fast ramp, I didn't show data on this, when you do a fast ramp, we certainly see a combination of excitations from ground state to first excited state, but also from first excited state to second excited state, and so forth. Now it turns out in this spectra, if I can get back to it, for this particular problem of the infinite range Ising model, these differences are nearly exactly the same. So all of those different, many higher order excitations lie right on top of each other, and they're very small energy differences. Very hard. It would be very hard to separate those out. But in general system, it won't be the case. A two-particle excitation will be different than two single-particle excitations. And there's no signal that you're going to get from analyzing this time series that is going to tell you which one it is. And it'll tell you that there's an energy excitation of some kind, but it won't even guarantee that it's an excitation from the ground state to the excited state. Now, if I follow things via continuity, by carefully doing this at a bunch of different magnetic fields or whatever the parameter is that I'm varying in the experiment as I'm moving through, then maybe by continuity I can sort of see that initially what I'm going to be getting are excitations from the ground state because that's what I should be exciting from. But then as I get enough of those out there, I will start to see deviations which are coming from even higher excited states and so forth. So there's some information, I think, from the amplitude of how big the Fourier series amplitude is that's going to have to be used in some fashion to tell you about this information. But I think it's a really hard problem to figure out how to do that in a precise way. So I think no matter what, you're going to end up having some guesswork in trying to figure out how that works if you're really looking at data and you have a system that you can't calculate.
Okay, yeah. Ooh.
If you were interested just in the size of the critical gap, are there even more relaxed constraints that you can put on the amount of data that's necessary to collect compared to wanting to know about even higher excited energy disciplines?
I don't see how that works because the high energy splittings, of course, they tend to have very low amplitude because it's harder to excite them. But the high energy excitations are the ones that you'll see first because those oscillations are the short ones in your time window. It's the longest, so you just have to go out long enough until you're properly seeing it. So I don't know that there's any shortcut to get directly at that from this technique.
Okay, but the resolution of the points, even if you need a longer time, can that be relaxed?
I think the question is, can I get a good observable that collects, that doesn't throw out data and collects as much of the data as possible so I can get the best statistics? And I think we need to think about what that might be. Because I think that's really at the key issue that one wants to try to capture is getting the, if you do a whole series of experiments, you want to try and use as much of that data as possible. In these simulations, I'm throwing out 99% of the data. That's why it takes a long time. Okay, that's not an efficient way of doing it, but we haven't really addressed that in a very coherent way yet.
Okay, if there are no further questions, I thank you again.